Hi, I'm going to do a two-dimensional Coulomb's law problem, and I'm going to do it a way that has a little bit less math, and it takes advantage of some geometry of the situation. So there is another video doing it what I think of as my normal way, but a student showed me this way, and I'm in love with it, and so I thought I'd redo a couple of videos. So here are three charges. We've got a positive 8 nanocoulomb, negative 15 nano, negative 10 nanocoulomb. We have the distances there. And we want to know what the net force on this 10 nanocoulomb charge. So what is the net force on that 10 nanocoulomb charge? And what I recommend people do is start with drawing the forces that we know this is going to be experiencing. So I am this negative 10 charge. What do I feel from a plus 8 here? Well, opposites attract, so I'm going to feel an attraction up. So the force from the 8 is going to be acting upward. What do I feel from this negative 15? It's pushing me away. So the force from the 15 is going to be down here. And then I just need to know what those forces are. Add them up as vectors. Okay, so the force of the 15 acting on the 10. Well, that's just straight up Coulomb's law. So 9 times 10 to the 9. And my first force, or first charge is 15 nanocoulombs acting on a 10 nanocoulombs over the distance between them. Well, crap, we don't know that. And I'll just remind you, we don't put the negative signs in for these charges because Coulomb's law is actually absolute value. Coulomb's law only tells us the size of a force. It doesn't tell us anything about direction. So I don't care that there's negative signs in there on the charges. I have to look at the physical situation to know what direction it is. In this case, don't know. But I need to know what that distance is between the two. Okay, well, fine. I have a triangle. And I've got 3 centimeters. I've got 5 centimeters, and I want to know what this side is. Pythagorean theorem tells me that this is 5.83 centimeters. Okay, so I'm going to dump that in here. Centimeters, convert to meters. 0.0583, and then don't forget r squared in the bottom. All right, so the force of the 15 on the 10, if you do that, you should get 3.97 times 10 to the minus 4 newtons and acting down at some angle, like that. All right, then let's figure out what the force of the 8 on the 10 is. Same deal, 9 times 10 to the 10, and 8 nanocoulombs acting on 10 nanocoulombs at a distance of, okay, 8 on 10. So that's 3 centimeters, 0.03 squared. Okay, and that, oh, look at that. That's a 3 squared, which is a 9, so this is going to come out to be an 8 times something. 8.0 times 10 to the minus 4 newtons, and direction for that is straight up. All right, now that we know the size of these two forces, what we want to do is add them as vectors, because they're forces, they're vectors. This one's easy, it's straight up, but we need to know the x and the y components of this one. It's down and to the left, so we've got a negative x component and a negative y component. How can we get them? In my traditional way of solving, we would figure out what one of these angles is, and then the x component would be the cosine or the sine, and we could do it that way. But the cool thing is, we know that the direction of this force of the 15 acting on the 10 is exactly in the same direction as this hypotenuse of the distance triangle. So we have similar triangles here. I can say that my x component and my y component of my force. So the hypotenuse, the entire force is 3.97 times 10 to the minus 4. And I want to know my x and my y components. Okay, so instead of doing sine, cosine, blah, 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 similar triangles. 5 is to 5.83 as x is to 3.97. So 5 is to 5.83 as x is to 3.97. If we do that, we get an x value of 3.40 times 10 to the minus 4. And same thing with the y component. 3 is to 5.83 as y is to 3.97. 3 is to 5.83 as y is to 3.97. And the y component then is going to be 2.04 times 10 to the minus 4 newtons. No angle calculation needed, no sines, no cosines. I now have the x and the y components for this angled force, and I gotta be careful. This is a negative because it's going to the left, and this is a negative because it's going down. I'm just gonna put those reminders there. Left and down, and then I already know the x and the y components of this one. There is no x component, there's no horizontal part to this vector, it's all in the positive y direction. So at this point, I'm going to go back to what I normally do, which is put all the vectors into an xy chart, add up all the x's, add up all the y's, and then I can come up with my final triangle. So I'm going to erase and do that. All right, so let's put our x and y chart together. We have a couple of forces. We want to know what the x component is. We want to know what the y component is. And then we will add them up together. All right. We have, what do we have here? So the force of the 15, I gotta be careful, acting on the 10. And this is what I just calculated. So the x was negative 3.40 times 10 to the minus 4, but all of our exponents are the same, so I'm going to be lazy. And my y component is negative 2.04 times 10 to the minus 4. The F8, the force of the 8 acting on the 10, there is no left-right component, and it is all in the upward direction, so it's a positive 8.0 times 10 to the minus 4. Okay, good. Let's figure out what the sum is. So if we add up here, we've got a negative 3.4. If we add here, 8 minus 2, that gives me a positive 6.0. So my triangle for my total force, I'm going left 3.4 and then up 0.6. And if you struggle with how to make the triangle, think about it as literally walking a path. I'm going to go 3.4 meters, miles to the left, and then I'm going to go 6 meters, miles up, north, whatever you want to call it. And so our final is going to be what? The hypotenuse of this. And we can use a squared plus b squared equals c squared to get the net force, which I got 6.90 times 10 to the minus 4. Don't forget to put that exponent back in there. And we need an angle because, again, forces are vectors. We need to know what direction it is. Use the inverse tangent of opposite over adjacent. 6.0 over 3.4 to get me my angle. And the angle turns out to be, what do we got? 60 degrees. Okay, now you can't just say 60 degrees because if you tell me 60 degrees, I probably think, well, I'm going to start at 0 and go 60. So you need to give me 60 degrees north of west. You could give me plus 180 minus 60 plus 120 degrees. You could do 60 degrees above the negative x-axis. That would be another way. All of those are good, so long as you give the size and a direction. So that's a slightly quicker way to do these 2D problems that doesn't involve sines and cosines and angles. All you're using is this awesome trick of geometry of similar triangles. So I hope that's helpful. I'm kind of in love with this new new idea of this new way of doing it. So I will now do all of my solutions like this because dang, it's easy. I hope this was helpful.